Hi. Now that we know how differentials work, we know how to use them, we can broaden our definition of a differential. And today we're going to discuss total differential. Imagine a situation like this, that we've got some function, some z equals some function of x and y. Okay, look, the thing here is that both x and y are influencing the value of z, right? They both go through the same function actually, right? Function f, and each of these influences x individually, z individually. Okay, so look, in this case, when we calculate differential, we can calculate actually two differentials. Because look, now we have two possible sources of change in z. Look, so change in z, dz, in this case, can come from two sources. First, change in x, and second, change in y. Now, we need to evaluate impact of these two changes in x and y on z individually. So actually what we're going to use are partial derivatives. Look, in this case, we can say that if x is changing by some small amount, then z is changing by how much? Well, it's going to change by the value of derivative of the function f with respect to x. Or we can write this as simply fx. And look, similarly, if x is held constant, then change in z can only come from change in y, and then change in y on z can be evaluated using derivative df dy. So the second source of change here is evaluated using derivative fz. So we can simply write that dz is equal to fx dx, where fx is derivative of function f with respect to x, partial derivative, so assuming y is constant, plus fy, which is derivative of function f with respect to y, now assuming x is constant, times change in y. Okay, so look, now we've established that that a given differential can have more than one source of change. And look, imagine that we've got savings function, and the savings function is a function of income and interest rate in macroeconomic sense. So, in this case, we can say that change in the level of savings is equal to impact of income on savings, so sy, where sy is derivative ds dy, times change in income. Well, the second source of change is change in interest rate, of course, times derivative si, where si is simply partial derivative of s with respect to interest rate. So you see, we've been able, for this savings function, track out two sources of change. But look, now that we know how to do this for just two variables, we can go to the case of n variables. how will it work? Now, look, let's just say that y is a function of variables x1, x2, and x until variable xn. Now, you see, in this case, we have that y is influenced by variable x1, by variable x2, by variable x3, and so on until variable xn. So look, this time, the source of change, we've got n different sources of change. So the resulting change in y must come from change in x times impact of x1 on y, assuming all other variables are constant, plus the same for x2. Now we are assuming all other variables are constant. Well, derivative, partial derivative, df dx2 measures the impact of x2 on y. And we go on like this until the last variable, df dxn dxn. So look, this expression is putting down all possible sources of change of y, so all the independent variables here, while partial derivatives that we see over here are showing us what is the impact of each of these of changing each of these individual variable on y. And look, again, we can simplify this by writing f1 dx1, where by f1 we mean, of course, partial derivative with respect to x1. Then we would have plus f2 dx2 plus until fn, where fn denotes partial derivative with respect to n times dxn. So look, again here I could put f1, f2, f3 until fn. Okay, I hope you will not find it that complicated, because it isn't. Let me just show you just one more example. Now look, let's just say the quantity demanded is a function of price, makes perfect sense, customer's income, let's just say price of good, that is a complement, price of a good, that is a substitute, and interest rate on a bank, right? So look, again, I can write the change in quantity demanded is the sum of dP times dP. So change in price times the derivative of demand with respect to price plus di. So change in income times change in times derivative of quantity demanded with respect to income, and similarly over here dPc plus dPs plus di. And look, of course, we expect all of those things to influence quantity demanded. Price, definitely. Income of the customers, definitely, depending whether good is normal, inferior, luxury, the impact will be slightly different. Price of complements, of course, if it goes up, we will have drop in demand. If it goes down, we will have higher demand. In case of substitutes, the other way around. And finally, of course, the same with interest rate. Lower interest rate means it's easier to borrow money from the bank. Customers can afford more goods. And using total derivative, we can simply trace back all possible sources of changes in one variable as depicted separately for all the independent variables, the ones that influence quantity demanded. Okay, so this is it about total differentials. We're going to use them in a couple of cases, so we need to know how they work, but using them is pretty much very easy. So let's concentrate on a specific example that we're going to start since the next video.